Today we're going to assess the fit of our least squares regression line. Some important questions that we need to consider when we are talking about the least squares regression line are: 1. Is the line an appropriate way to summarize the relationship between the x variable and the y variable? Number 2. Are there any unusual aspects of the data set that we need to consider before proceeding to use the line to make a prediction? And finally, if we decide to use the line as a basis for prediction, how accurate can we expect the predictions based on the line to be? Graphical and numerical methods will help us answer these questions. So in order to assess the fit of the least squares regression line, we need to talk about the following things of our LSRL model. One is residual plots as well as residuals. Also, we need to determine if there are outliers in the data set. 3, are there influential points? And then finally, we need to discuss the coefficient of determination, which we have been able to find rather easily, um, our R square. We haven't talked about R square much yet, but we are going to in this video. So in my example here, I have the following. In a study, researchers were interested in how the distance a deer mouse would travel for food is related to the distance from the food to the nearest pile of fine woody debris. Distances were measured in meters. So I want to plot the points and draw a regression line on my data table. I already wrote the points in my calculator here. They are in list 1 and list 2. So now I want to find my least squares regression line as well as draw a scatter plot of my two variables. So recall that in order to find a least squares regression line, we have to store our regression equation into our y equals. That is done by clicking on vars, y vars, functions, and then choosing any of the y variables. Typically y1 works. Okay, so I calculate and it gives me my line of best fits as well as my correlation coefficient, and as I just described, the coefficient of determination, which we will talk about at the end of this video. So if I go to my graph, I have my data points plotted in my scatter plot as well as my least squares regression line. Now we can use the distance between the actual y values that we have in our data set as well as the predicted y that our line would give us. This tells us a lot of information if we find it. So first, let's talk about this distance. The distance between the line and our actual data points is called a residual. Residuals are calculated by subtracting the predicted y from the observed y. So you subtract the actual y that you have from your data set by what your model predicts. So yes, you will have to find what the model predicts y would be by plugging x in to your least squares regression line. The residual is the vertical deviation between the point and the least squares regression line. If it is above the line, the residual should be positive because we are subtracting our actual from our predicted, and it's above the line. If the point is below the line, the residual will be negative. Now, one important thing that our residuals tell us is that what it would be considered an outlier. So an observation is an outlier if it has a large residual. In order to exactly determine whether or not a data point has a large residual, you will need to first find the residual and also compare it to the least squares regression line on a scatter plot. So it would be important to draw a scatter plot as well as the LSRL in order to just see it. Residual outliers can be subjective from data set to data set. So as I stated, in order to find the predicted y, you need to plug in each x variable, each x data value into your least squares regression line. So each of these numbers are plugged into your formula in order to find the predicted distance traveled. Once you have this prediction, you are able to find your residual by taking the difference between the actual and the predicted. Now, residual plots residuals do more than just give you an estimate of the actual versus the predicted values for your model. You can also plot residuals. A residual plot is a scatter plot in which you have the x value of your dataset as well as the residual paired together. You can also do this for predicted y values as well, and it should give you the same value. And here's the purpose of it. The purpose is to determine if a linear model is the best way to describe the relationship between the x and y variables. And here's how you can discover that. If no pattern exists between the points in the residual plot, then the linear model is appropriate. So what exactly does that mean? Here I have two residual plots. As you can see on the left one, there is no pattern shown. All of the plots are scattered randomly. This indicates that a linear model is appropriate because there is no function that you can see within the residual plot. However, on the right side, you can sort of see a pattern there. You can actually see a clear curve here. Since this residual plot shows a curve, we can conclude that a linear model would not be appropriate for the residual model on the right side. The model that we actually would want to use relates to the pattern that we see here. We would want to use a quadratic regression instead of a linear regression. So, I suggest that you pause the video here in order to jot down notes to plot residuals on a calculator. Otherwise, I'm going to quickly show you how to plot it on a calculator um, without going back to this screen to show you the steps. So, in order to plot a residual, you would want to first, let's just get rid of our least squares regression line, and then you will want to go back to your scatter plot. Okay, so as I stated, the x value in our scatter plot for residual plots will just be our x variable in our data set, whereas our y variable will be our residuals. Now, in order to find a residual, you have to first find the prediction of every data point and then plug it into the calculator, which can be rather tedious. Our calculators actually find residuals for us. In order to go to a residual, you want to first make sure that you have the Y list highlighted, and then click on second and then stat to go to list. Now, you should instantly be able to see resid, which represents residuals, and we want to click on that. Okay, so now that we have residuals in our Y list, we're now ready to graph it. So make sure you click on zoom 9 to see the graph. And voila, we have our residual plots on our calculators. And we can clearly see from that previous data set that a linear model is appropriate because there is no pattern. Don't try to force patterns. I know some people would probably suggest that this looks like a curve, but it has to be a really, really clear pattern, okay? So, I have a second example here that states the following. Let's examine the following data set. The following data is for 12 black bears from the Borough Forest. What we're measuring here is their age compared to their weight, okay? So, I already have this data set in my calculator as list 3 and list 4, okay? So what I want to do is draw a scatter plot here. So if I turn on my plot 1, which already has list 3 and 4 in it, I'm ready to draw a scatter plot on my calculator. So you want to click on zoom 9, and we have our scatter plot. Now, What we notice here is that as x increases, y does tend to increase. However, we have a really strong point on the outside of this data. It is on the far right side and it's not very close to the other data sets. So what does this say about our data set? We would consider this point an influential point. Influential points affect the placement of the least squares regression line because this point is going to change the direction of the line so that it also fits with the line. So what influential points do is they affect the slope. They have an effect on the slope. It does follow the general pattern that as x increases, y increases, but it increases just a bit too much compared to the rest of the data sets. And therefore, this point could change how our model predicts the weight of bears based on their age. And finally, R2. R2. What does this coefficient of determination mean? So the coefficient of determination gives the proportion of variation or differences in y that can be attributed to an approximate linear relationship between the x and y variables. What this is saying is we have a percentage in which the differences of our y values are attributed or impacted by our least squares regression line, the relationship that it has with its dx variable. Meaning, the higher the coefficient of determination is, the more we know about the differences between our y values, why our y values vary so differently between each other within this data set. So there is a reason why the coefficient of determination and the correlation coefficient have a relationship. The higher the correlation coefficient, the more we know about the differences in our y values. So for our bear example, if we find our coefficient of determination, remember, we always want to store a line that best fits in our equation just so that we can see it now. Then here's what we know. We know what the slope and the y-intercept means in terms of this problem. And we also know what the correlation coefficient tells us. It tells us that we have a weak positive relationship between these two variables. So there's a weak positive relationship between the age of bears and the weight of bears. And now we also have the coefficient of determination, which is 24.4%. So what we can say here is that the differences, 24.4% of the variation in the weight of bears can be attributed to the linear relationship between the weight and age of bears. So this means two things. We know that a quarter of the differences in the weights of bears is attributed to our linear model. But we also know that 75% of the differences is unknown. It's because of a lot of other different variables. Probably things such as the species of bear or the gender of bear or the amount of food they consume or even the time of year that a bear is seen. So, our coefficient of determination helps us to clarify more of what we know about our linear model. The higher the percentage, the more we know about the relationship between our two variables.